This is the pre-lab talk for experiment number 3, determining the formula of a hydrate. The goals for this experiment are to determine the chemical formula of a hydrate in 2 different methods. The first method is we'll take the non-hydrated or anhydrous form of the compound and add water to hydrate it and form the hydrate. And then in the second part, we will take the hydrated form of the compound and drive off the water by heating in a crucible. We're also going to introduce one statistical way of looking at error, the use of the standard deviation of the mean. And finally, we get to use a new experimental technique, heating a crucible with a Bunsen burner. For today's safety pause, we note that anhydrous copper sulfate is a very fine powder that can also become an irritant. So you want to be very careful. You don't want to breathe in any of the solid, and you also want to keep a lid on that solid at all times. I always want to note when we use crucibles and heat them that hot crucibles look exactly like cold crucibles. This means that a crucible that might appear to be cooled down may not actually be cooled down. So you want to make sure that you exercise great caution when handling glassware or porcelainware in this case after it's been heated. We're going to be very careful in this experiment to cool down our crucibles for an appropriate amount of time so that we can safely handle the crucible. And even then, we're going to use crucible tongs. Okay, in all cases, when we're heating our hydrate, when we're working with the anhydrous copper sulfate, we want to make sure that we keep lids on at all times to avoid being exposed to fumes of these toxic chemicals. And finally, since copper 2 sulfate, both in the hydrated and non-hydrated form, are environmental hazards, we'll be collecting copper 2 sulfate waste in a special waste bottle at the end of the experiment. Okay, so important concepts for this lab. The first important concept is all calculations will be done using the mole concept. So we're not really doing any stoichiometry here. We're simply taking a look at the mole concept itself. Also, we're going to talk about hydrates in the context of empirical formula or formulae. So the first thing we want to talk about is the mole concept. So you're going to be doing some pretty simple calculations that involve the mole. So the main thing you're going to actually be doing here is taking the mass of a substance and calculating the moles of that substance. And you'll do that by dividing the mass by the molar mass of the substance. So the molar mass, just to remind you, is the mass of 1 mole of a compound. You can calculate the molar mass of any compound by adding up the molar masses of the constituent elements, and those masses can be found on the periodic table. So, for example, water, the mass of oxygen is about 16 grams per mole. And for hydrogen, each hydrogen atom in water has a mass of about 1.008 grams per mole. And so if I add those up, so 2 times 1.008 grams per mole plus 16, and I round that to 4 significant figures, that's going to give me about 18.02 grams per mole for our molar mass of water. So that's an example of, thinking about how to calculate a molar mass. And you do want to make sure for this experiment, since we want to get very highly precise results, that you don't round off your molar masses of the atoms by too much. You should use 4 significant figures or more in your molar mass calculations. You don't want that to be what limits the precision of your final answer. Okay, so let's talk about hydrates. So a hydrate is an ionic compound that contains water molecules in its crystal structure. And so we actually represent those water molecules in the formula for the hydrate. So for example, in experiment 1, we used cobalt chloride hexahydrate. Might not have meant very much to you at the time, but now we can think about it is that, so for cobalt chloride hexahydrate contains those water molecules in its crystalline structure. And this is an empirical formula for the hydrate. So this is a simplest formula for a hydrate. So anytime you see a formula for a hydrate, it's going to be an empirical formula. And that 6 means that for every 1 mole of cobalt chloride used, or cobalt chloride we have, there are 6 moles of water. So if we know the moles of water and moles of cobalt chloride in any sample, if I would take that cobalt chloride hexahydrate and drive off the water, which we were actually doing in experiment 1, and I could separately calculate the moles of water and the moles of cobalt chloride, if I take this ratio, I'm going to get 6. So that represents that empirical formula. So in this experiment, we're going to look at the empirical formula for a copper 2 sulfate hydrate. So we're going to determine that experimentally. All right. So another important concept we're going to introduce here is the standard deviation of the mean. Okay, so to do this, we're going to look at some data that I collected from one of my labs in the past that I've taught for experiment 2. So this is their 2 milliliter data. This is a histogram of their 2 milliliter data. So in a histogram, we're plotting the number of times a density value gets in a certain interval versus that's on the y-axis. On the x-axis, we're plotting density. So this pretty much shows the spread. A histogram shows the spread in density values calculated from the student's 2 milliliter data in experiment number 2. Okay, so one thing that you calculated in experiment 2 is the average. So you add up all of the densities and divide it by the number of measurements. So if you make 3 measurements in calculations of density, you add them all up, divide them by 3. So the x on the histogram represents the average density, which is 0.986 grams per milliliter. Okay, so in experiment 2, you also looked at the spread in data, which tells you about the precision. So if you have a smaller spread in data, the precision should be higher than if you had a large spread. And you probably saw that your 2 milliliter data should have probably had a larger spread than your 20 milliliter data, and that's because with that extra significant figure on the larger mass of water, you can get things a little bit more precise. So we can use a spread, just taking the largest number minus the smallest number. We can also look at the standard deviation, which is a statistical spread in data. It represents, I believe, about 67% of the data fall within plus or minus the standard deviation. So I can represent that on this plot with this blue arrow. So the standard deviation for this data is plus or minus 0.0583. which means that the majority of the data here, about 67%, you can round that up to about 70% of the data fall within plus or minus 0.0583 from the average. Okay, so this is a means of looking at spread. So smaller standard deviation means our data is not as spread out and is more precise. So what does the standard deviation of the mean tell us? So to get the standard deviation of the mean, you take the standard deviation and you divide it by the square root of the number of trials. So if you do 3 trials of an experiment, you divide by the square root of 3. That's a common number of trials in our experiments. So I calculated the standard deviation of the mean for this data, and it's smaller. It's about the width of the x there. So it's 0.009 grams per milliliter. This tells us the uncertainty in the average value. So there's a couple of things here that are important. The standard deviation of the mean depends on the spread in data. It also depends on the number of trials. So this is why we do multiple trials. You want to have, if you have multiple trials, the uncertainty in your average value goes down. You also want to be as precise as possible with your measurements by just being careful and to minimize those systematic errors so that your standard deviation is also small, and that will maximize your error. Okay. Another thing you want to note here is that when I quoted my standard deviation of the mean, I only did it to one significant figure. And the main reason behind this is that anytime you do measurements or do calculations for measurements, your last digit is always the most uncertain one. It's the one you usually are rounding off, or it's that hardest to measure or estimated measurement that you're making. So there's no reason to quote the standard deviation of the mean to more than one sig fig. So we'll always do that. So how do we use this? So if you're going to do a final quote of your numbers, I would report my density as 0.989 plus or minus 0.009 grams per milliliters. So one thing you'll want to notice here, it worked out perfectly, is that once you round your standard deviation of the mean to one significant figure, then your average value should be quoted to no more than the same number of decimal places as the standard deviation. So since I went out, or standard deviation of the mean. Okay, so since I went out to the, let's see, thousandths, so 10,000th place, right? No, thousandths place. Then I want to make sure that my average is also rounded to the thousandths place. Okay, so that's standard deviation of the mean. In this experiment, we're going to actually use it to compare our two methods. So is heating and driving off the water an equivalent way to figure out the empirical formula of the hydrate to adding the water to the anhydrous compound? Okay, so let's take a look at some procedural points. So for part 1, let's go over some of the balance rules. So we are going to be at measuring out a solid this time. We talked about some balance rules for experiment 2, and a lot of those are still at play. You don't want to add any chemicals directly in a container that's in the analytical balance. You want to make sure that you're tearing, so things like that. The added thing here is that we're going to be using the top loader balance and the analytical balance to make our mass weighings. And if you look at the balance rules in Appendix A, what you want to do is, what we're going to be doing, we'll use the top loader balance to get a rough weighing of our solid sample. And then we'll move to the analytical balance to get a more precise weighing. Okay, so that's how we'll be using both balances to get our weighings. And this is to keep the analytical balance from being damaged. So we're never going to add solid directly using the analytical balance. Okay, part one has a lot of trial and error. Basically, I have to, by sight, be able to tell if I'm adding water to hydrate my anhydrous copper sulfate sample. I want to get a blue solid. I don't want to add too much water, then it looks wet and it's no longer, a solid. It's becoming a mixture. So I don't want to do that. And I don't want to add too little. And I can't really tell right off the bat except by eye. So I'll be comparing the hydrated form to the compound that I'm hydrating to kind of compare colors. So there's a picture in your procedure to sort of help you to, kind of see the difference in color. So the anhydrous form is a very extremely pale blue color, and the hydrated form is a brilliant blue color. All right, so for part two, we talked about, being careful with heating the crucible. So there's the experimental setup that I'll be using. So the Bunsen burner will be about an inch or inch and a half or so from the iron ring, and I'll be setting the crucible in a clay triangle, and the clay triangle will be in an iron ring. So a couple of things are important here. I will not be adjusting anything when I start heating. So once things get heated up, I'm going to make sure that I don't touch anything to make any adjustments. Always make adjustments before you start heating because hot metal burns. We'll be lighting the Bunsen burner. And the same thing we talked about with the crucible. Hot crucibles look like cold crucibles. We don't want to assume that the crucible's cooled down. So except for the very beginning when I'm setting things up, I'm not going to actually touch the crucible anymore. I will only use crucible tongs, and that's a safe way to go. Okay. So it's also important, other than safety reasons, it's also important to make sure that our crucible is cooled down completely before weighing. You cannot get an accurate mass of two things that are hot. The convection actually messes with the mass measurement. So I'll be making sure that the crucible is completely cooled down for about 10 to 15 minutes before I go on and weigh things. All right, let's talk a little bit about the analysis. So I made a flow chart. So the goal of this experiment in both parts is to determine N in our copper sulfate N-hydrate formula. So we need two things. We need to know moles of copper sulfate, and we need to know moles of water. And that information is all coming from our masses. So in both parts 1 and 2, you'll need to get the mass of your unhydrated copper sulfate. So in part 1, that's going to come from your initial weighing of anhydrous copper sulfate. In part 2, this is going to come at the end of the experiment after you have done your final heating. So that'll tell you when you weigh that should only be copper sulfate at that point. Okay, so once you get that, then you can use it to calculate moles of copper sulfate using the molar mass of copper sulfate. So that's something that I'll actually have you do in your pre-lab for practice. Okay, so same thing with water. You need to know the mass of water in part 1 that you've added. So you'll subtract the mass of your beaker, beaker, micro spatula, and hydrated sample from, you'll take that, subtract off the mass of the beaker, micro spatula, and unhydrated sample, so that should equal the amount of water that you added. In part 2, you'll take the difference between the masses before and after heating, and that'll be the water that's been driven off. Okay, so once you get the mass of water, you'll also convert that to moles. We already said that the molar mass of water is about 18.02 grams per mole. Okay, so once you have your moles of water and moles of copper sulfate, you'll take, in both cases, you'll just take a ratio. So N will be moles of water over moles of copper 2 sulfate. Okay, and we'll be able to see, if it's the same compound that we're dealing with, they should be about the same number, but we'll see how well that these two things agree with one another. Okay, go forward and do chemistry, or watch chemistry.